So I'm going to do a little bit of quantum mechanics now. This is going to be the solution to the 1D infinite potential well problem, or the particle in a box problem. If you've already heard of this, you might want to skip ahead past the introduction. Okay, so quantum mechanics is a bit different to classical mechanics and how things work on a macroscopic scale. On a microscopic scale, things behave differently. One idea is the Heisenberg uncertainty principle, the idea that you can't know both the momentum and the position of a particle to infinite precision, both at the same time, of course. So the idea that we should be dealing with probabilities in quantum mechanics rather than anything more tangible is perhaps not too surprising. The crux of all this is an abstract quantity called the wave function, which describes how quantum systems work. The wave function itself doesn't have any meaning that is non-abstract or totally relevant, but the modulus of the wave function squared does have a physical meaning, and it can be expressed in terms of a probability. In fact, one of the modern interpretations of quantum mechanics is that the square of the modulus of the wave function is a probability density function, or proportional to the probability that a particle exists at a particular point. So this probability interpretation is widely used. So for instance, in this diagram here, where I've got wave function on the y-axis and the position on the x-axis, at places where the wave function is equal to 0, there's basically no probability of finding the particle. At places where the wave function is positive or negative, there is a probability of finding the particle that's non-zero, because of course you've got to square it. So this is a problem where I'm constraining a particle into a box with infinite potential on both sides. An analogue of that in the classical world is where you might have a ball inside a box with infinitely high walls on both sides, so the ball's constrained inside the box. Similarly, we've got an electron or a quantum particle constrained by infinite potentials on both sides, and the potential inside the box is 0. So the equation that governs how these systems work is called the Schrödinger equation, or specifically the time-dependent Schrödinger equation. And it's time-dependent because the wave function here is a function of both position and time. This equation is somewhat empirical, so I'm not going to derive it, but you could use this equation to solve for the solutions of this particle in a box problem, and that's what I'm going to do. And the maths may look hideous, but it's actually not. It's just that the symbols are somewhat, archaic. Lots of Greek symbols, but it's not that bad. So this differential equation, the idea is to solve it, and for this particular potential that I've just mentioned, this piecewise potential that I just mentioned, and we'll get a set of solutions. And that's basically what I'm going to do now. The method of solving it is called separation of variables, the idea being that you take the time-dependent wave function and split it into a wave function in terms of just position and a wave function in terms of just time, which is f of t here. And this little psi of x is the wave function just in terms of position. So a substitution has occurred between the time-dependent wave functions here, psi, and little psi times f of t, psi of x times f of t. So the assumption that this wave function is a product is not maybe totally general, but it certainly helps to solve the equation. Okay, so that's the assumption there. That's done. The next steps are just a little bit of algebra. The idea here that since we're taking the partial derivative of this thing in the brackets, and a partial derivative is different to a full derivative in the sense that it's only in terms of the variable directly that we're referring to. So this partial derivative with respect to x, the partial squared derivative with respect to x, is only thinking about x, or something that's a function of x. Since this function of t has got nothing to do with x, it's not explicitly defined in terms of x, it's not relevant. The derivative is not with respect, has got nothing to do with this. So it's just a constant to all intents and purposes, so it can be taken out, which is what I've done here. And of course, similarly, this derivative with respect to t has got nothing to do with this wave function in terms of x. So similarly, this can be taken out like that. The next step is definitely algebraic. But divide both sides by the product of psi of x and f of t. Thus, so obviously f of t cancels and we end up with a psi of x on the denominator. This thing cancels completely here, and we end up with an f of t here. This is equal to e, a constant. The reason that it's equal to a constant is because we've got a function purely of x on one side and a function purely of t on the other side. And since x is not a function of t itself, the only way this can be true is if they're both equal to a constant, which is being called e. E has a special significance in itself, which I'll come to later. Okay. So the right hand side is very easy to solve. It can be done in a few easy steps. So just looking at this little bit of the equation here, IH over f of t, df of t equals e dt. So what I've done is multiplied through by dt. So I've got the dt on this side. I notice that these are full d's. The reason being that since we're just dealing with f of t, the only variable involved here is t. We don't need to use the partial derivatives because everything is just in terms of t. So we can integrate both sides, and this is just a simple variable separation integral. Of course, it has a simple solution as well. The integral of this side, since we've got a 1 over function, is going to be the log of that function, natural log of that function. Obviously the IH is still multiplied through it, and that is equal to e t plus c. This is easier to express nicely if we express c in a better way. So what I've done is I've taken c onto this side, divided through by IH, and then defined log of a as being equal to c divided by IH. And this is just an arbitrary switching of variables, but it makes the equation much easier to solve. So that's why I've done it. Well, it doesn't make it easy to solve, it just makes it nicer. Nicer to express in a nicer form. So this can be expressed in terms of log rules. So I've got log of f of t over a. A is just a constant that came from the constant integration here, c. And of course the et divides through by the IH, and 1 over I is equal to minus I. That's easy to prove. You just multiply both denominator and numerator by I. Of course I over I is equal to 1. If you do that, you're going to get minus I on top here. Raise both sides by the exponential e. So e to this, get f of t over a is equal to e to the power minus eti over h bar. And then we can multiply this through by a. So we get f of t. So the wave function to the time is equal to a e. So negative eti over h bar. So that's solved, which is why I put it in a box. Now we come to the position wave function, which is somewhat harder to solve. So I've just copied this down to here. That's just copied. Okay. Next thing is to multiply the whole equation through by psi of x. So it disappears from here, and it appears here, and it appears here. At this point, I'm going to say that u of t is equal to 1 because it makes the problem so much easier if we're dealing with a potential that is time independent. I think actually I've already assumed it somewhere, but if the potential is time dependent, it makes the problem so much more complicated. And then this specific example that's not done, we're going to assume it's time independent. You can find this particular example, the 1D infinite potential well problem. It's very pervasive everywhere, and this is generally what's accepted, that it's going to be a time independent potential well. Okay, so we end up with this. This is in a box because it's another important differential equation known widely as the time independent Schrödinger equation, and it's independent because it's only in terms of x, it's not in terms of t. So this differential equation is Schrödinger equation just in terms of x. So this is why it's termed time-independent Schrodinger equation. And actually, in my picture here, I've got the little psi of little psi. So I've got my time-independent psi wave function there. Okay. Of course, since there's no t here, this is actually an ordinary differential equation rather than a partial differential equation, and ordinary differential equations are much easier to solve. Actually, this has constant coefficients as well, so it could be solved in the standard way that second order differential equations are solved when they have constant coefficients. We assume that the solution is equal to e to the power of lambda x, where lambda is the root of the equation, the solution. Instead, these should be these shouldn't be superscripts. These are the derivatives. So I've differentiated psi of x with respect to x to get lambda e to the lambda x, and then I've done it again to get lambda squared e to the lambda x. The second derivative of psi with respect to x, and you substitute this guess, this guess that the psi of x is in this form, back into this equation, the time-independent Schrodinger equation, to get this. We've got the e to the lambda x here, and of course you assume that e to the lambda x is not going to equal 0, so we can divide through by this, because you don't want to miss any solutions. So when you divide through by something, you've got to make sure that it doesn't equal 0, because divided by 0 is a bad idea. So e to the lambda x is not going to equal 0, because that would imply that lambda is equal to negative infinity, which is not really a sensible solution. So I'm going to discount that, and we're going to end up with this, which is an algebraic equation in terms of lambda. So of course, rearranging, very simple to arrange, e minus v divided by minus h bar squared over 2m turns out to be this. This is the solution of lambda, and of course now the solution of the time-independent Schrodinger equation is equal to e to the lambda x, so it's equal to this. I'll explain the n later. The n turns out to be significant later, the n subscript here. It's obviously, since it's a second order differential equation, we can have a sum of solutions. This could be a negative or a positive, because a square root of a number has a negative answer and a positive answer, so that's why I've got two solutions here. This is linear. A second order differential equation is linear. It's a linear equation, so we can have a linear combination of solutions. And the reason for this is because when you substitute any one solution in, you're going to get 0. You've got an equation that's in terms of this thing. You've got an equation that's in terms of a second derivative and a single thing psi in terms of x, and that is equal to 0 when you take this onto the other side. So you're going to end up with solutions that go to 0, so you can of course add them together. So that's fine to do. And c and d are the constants, because these constants don't affect the solution, because when you substitute them back into this equation, the constants are not going to be affected by the differential operator. So there's two solutions, the negative one and the positive one, and they can be added together in some combination. That's the maths done, and now it's time to look at the physical solutions and what's sensible. See if we can determine C and D, and the answer is yes. It's done by looking at the problem itself. So of course, inside the box, which is this, the potential is equal to 0, I said that earlier, and outside the box, which is less than 0, x is more than L. L is the length of the box, of course. L is this value here. Potential is equal to infinity, which again I said earlier. So now look at the form of the wave function outside of the box, which is this one. Okay, so I'm going to let these I'm going to change the letters of these constants just to keep everything as unambiguous as I can. In this case, since the potential is equal to infinity, we substitute infinity into this lambda, which is something I don't like doing, but it's really a limit as something tends towards infinity. But it's all just for the purposes of looking at what happens. It's I can do this just crudely, and of course we're going to end up with since we've got a negative sign on here, we're going to end up with a negative infinity and a positive infinity bit here. Two solutions again. This one obviously blows right up to infinity, which is saying that the wave function outside of the box is equal to infinity, which is really really doesn't make too much sense, and it's something that I don't really want, because it's going to mean that I'm going to end up with a probability greater than 1, because the wave function is infinite, and when you sum it, when you integrate it over all space, you want it to equal 1. So this part of the solutions is not really sensible. So I'm going to say that this is not a sensible solution. This part, however, is sensible, because e to the negative infinity is 0. So the fact that the wave function is 0 outside the box is perfectly sensible. So I'm going to say that the wave function outside the box is equal to 0. Perfectly sensible solution. And now comes to determining C and D physically inside the box. Of course, outside the box at 0, it's also equal to 0. What we're doing is taking a part of the wave function that's outside the box at 0 and a part of the wave function inside the box at 0, because at the exact point of 0, the wave 0 is a point where you've got the wave function inside the box. It's at one bound. It's on the right of the outside of the box, and on the left of the inside of the box. So we've got to consider both bits of the wave function, the outside bit and the inside bit. Of course, the outside bit at 0 is equal to 0, because we've said that any any outside part of the wave function is going to always equal 0. So that's just done now. And of course, inside the wave function, oh, I've gone too far, so I'm up here. And inside the box, it's also going to equal 0, because that's by continuity. If it didn't equal 0, then we would have a wave function that isn't continuous. So since it has to equal 0 outside, you would want it to be 0 just a little bit inside as well. When I say just a little bit, I mean infinitely close to this boundary. Otherwise, the wave function is not continuous, and you're going to end up with some discontinuity, which isn't thought to be it's not really physically reasonable to have this sort of discontinuity. So the justification for this here is that it's got to be continuous. The wave function's going to be continuous at those points. Okay, so this is looking again at the inside part of the wave function, the part of the wave function inside the box. Of course, v of x is equal to 0 inside the box. That's all I've done there is let v equal 0, because it's inside the box. Okay. I've got a negative. I've got a negative 1 inside here that's multiplied through by everything. And you can take the square root of negative 1 out and make it into an I. Yeah. Again, simple. That's just definitions and terminology there, but it makes the whole idea easier. Again, this is the continuity thing. At the edge of the box, the wave function on the outside is equal to 0, and the wave function on the inside at 0, when x is equal to 0, of course, is also going to equal to 0. So substituting x is equal to 0 into this part, which is the inside of the box, so substituting 0 into here, we get e to a 0, which is a 1, so these bits disappear, and we end up with c plus d, which is equal to 0. So d is equal to negative c inside the box. Given that continuity condition, that's the physical condition, it's got to be continuous, implies that d is equal to negative c. Okay, so substitution, I'm going to get rid of d by just calling it negative c. So I've done a substituted d for negative c here. At this point, I'm going to use De Moivre's theorem, which allows you to express complex exponentials in terms of sines and cosines. Namely, e to the I theta is equal to I sine theta plus cosine theta, which is what I've done here. Theta, of course, is everything except the I. So I've got ended up with c cos of this nasty thing plus I sine of the same nasty thing, and then minus cosine of that nasty thing minus I sine of that nasty thing. So that these two parts are from this term, and these two parts are from that term. Of course, cosine of minus anything is equal to the cosine of that thing. Cosine of theta is equal to cosine of minus theta, because the cosine function is symmetrical. So cosine of a positive number is equal to cosine of the negative of that number. So this term here is identical to this term because of that. So these two cancel, and we end up with the sines. And of course, by the similar reasoning, the sine of a negative something is equal to the negative sine of that of the positive of that something, because the sine function is antisymmetrical. So sine of negative theta is equal to minus sine of theta. Okay. So this term is actually equal to this term. So we're going to end up with a negative 2i sine of this horrible thing, multiplied through by c. So we get this, which is not very nice, but it's physics, I suppose. For some reason, I've written this out again, just to emphasise that outside the box at okay, this is L being this point here. Same logic, really. Same logic. It works at 0. It's got to work at L as well. So the outside part of the wave function, this region here at the point of L is going to equal 0, and just as the inside part of the wave function at this point L is also going to equal 0. Again, so the point 0 and L are the only 2 points where the outside and the inside part of the wave function overlap, of course. So yeah, okay. Again, so this is the same reasoning, except we're looking at L rather than 0. Okay. So, substituting L into the inside part of the wave function, because this thing is the inside part of the wave function, substituting x equals L here, because I've just said that it's got to equal 0 because of the continuity. This thing has got to equal 0. Okay, so I'm going to divide through by 2ic. If c equals 0, then the fact that the wave function is if this prefactor equals 0, then that's a trivially obvious solution anyway, because the wave function equaling 0 everywhere does trivially satisfy this equation. When everything's 0 everywhere, that does trivially satisfy it, but that's not a very interesting solution. So what the maths is telling us here is that there is a solution where the wave function is 0 everywhere, but it's not really the solution that I'm looking for, but it is also a solution, so I don't have to worry too much about dividing through by 2ic here. So I'm just left with sine of this horrible thing is equal to 0, and of course that's true if this thing is equal to n pi, because sine of any integer multiplied by pi is equal to 0. So sine of pi is equal to 0, sine of 2 pi is equal to 0, sine of 3 pi is equal to 0, and so on, and sine of 0 is obviously equal to 0. Yeah. Obviously, so this applies for any integer from minus infinity to plus infinity. So I end up with this condition here. It might be worth pointing out. So this allows us to work out what E is, of course. E was the arbitrary constant that allowed us to change from the time dependent to the time independent wave function. The interpretation of E is the energy. Try and justify that. Obviously, it's got to have the same units as V, because because in this physical equation, each term in the sum has got to have the same units. So E has got to have the same units as V, and V is an energy, it's a potential. So E is also going to be some sort of energy, and the interpretation is that E is the total energy of the system. That's the interpretation behind it, and I've just tried to justify that loosely, why E is considered to be the energy. So actually, this it also implies that this thing is also a type of energy term, this thing here, and it's something called the Hamiltonian, which is not really energy, but it's a little bit like it. So this is the total energy, this is the Hamiltonian, this bit's the potential, sort of, you know. This is one way of thinking about it. But anyway, E is the total energy. So rearranging this, it's just an algebraic equation times by h divided by l, square it, and divide by 2m, you get this. E is equal to n squared pi squared h bar squared over 2ml squared. And I'm going to point out what h bar is, because I haven't pointed out what h bar is yet. H bar is Planck's constant divided by 2 pi. Yeah. Because it's sometimes written like this. So if you substitute Planck's constant divided by 2 pi, and then you can get this thing as well. That's an alternative way of writing it in terms of Planck's constant, which is one of the fundamental constants of the universe, really. So that's a different way of writing it. But we divide h Planck's constant by 2 pi so much that we write it as h bar just for convenience. Okay, so worked out what the energies are, and the energies can depend on what n is. So there's lots of different energies, lots of different energy solutions. I suppose each one of these waves has a different energy associated with it. So, but we haven't actually worked out a solution for psi, the wave function specifically. The way that you do work out a solution for psi is a method that I talked about earlier, that it has to be, it's a probability interpretation. The idea that you square the wave function and add all these probabilities up from minus infinity to plus infinity, it's going to equal 1. The probability over the whole space is going to equal 1. The total probability is always equal to 1. Of course, this isn't psi, this isn't quite the wave function squared, but it's basically the wave function squared. This is just the complex conjugate of the wave function multiplied by the wave function. So it's the modulus of the wave function squared, because the wave function can be complex. So you've got to take into account the fact that the wave function can be complex, so you're going to use its modulus rather than just the wave function squared. Since the wave function is 0 outside the box, we can just ignore that because the sum of 0 is just 0. So I'm going to look at L instead of, so I'm going to look at between L and 0, because that's the only where, that's where the wave function is non-zero, of the part inside the box multiplied by the part inside the box, the complex conjugate part. So the integral of that is going to be equal to 1, and I think I've just copied that twice. Okay, I don't know why I've done that. Anyway, this is the solution that we came up with this constant that wasn't solved. So I've just done that. The irritating thing here is, of course, so that this side is complex conjugate. That's why there's a minus sign on this side and there's a plus sign on this side because of that. And I've got C star here and C, and these are different because C is going to be complex, which is what we really want, because we want this whole factor to be real. Otherwise, we're going to end up with a complex solution, which isn't going to be too helpful. Anyway, I'm multiplying this by this, you get 4C C star, complex conjugate of C, integral of sine squared of that whole thing dx. This is easy enough to integrate using this identity here. We know that from trigonometry, cosine of 2z, for z is just some arbitrary variable. Oh god, I've used the word arbitrary so many times in this video. Is equal to cosine squared z minus sine squared z. And then using the Pythagorean identity to express cosine squared of z in terms of sine squared, we end up with 1 minus 2 sine squared z. Rearranging, we get sine squared z is equal to 1. So I've just taken these two parts here and rearranged to get 1 minus 2 cosine of 2z over 2, and then this is really easy to integrate. So I've substituted z for that horrible thing. And then integrated. 1 integrates to x, and cosine integrates to sine divided by that horrible thing there. Just integrating. And integrating between L and 0, of course. Thankfully, this term goes to 0 because, well, actually, I'm going to show why it goes to 0, but okay, hang on, I'll show why it goes to 0. So I've substituted L in here. Sine of 0 is obviously 0, and x is equal to 0, so I can just ignore those bits because they're 0. So this is just going to be equal to this. Just the L parts are useful. And then obviously, since we worked out what the energy was earlier, we substituted the energy for this thing that was worked out here. It gets horribly nasty, but it's not. The math isn't particularly difficult. It's just horribly tedious. And then this stuff cancels out a bit. I know I'm getting lazy. I should probably explicitly say where it cancels out with what. Yeah, okay. This thing cancels out, and we end up with this 2 CC star the bit on the outside. L minus 2 m's cancel. This L squared under the root cancels with this L. This H bar squared under the root cancels with this H. And we basically end up with just a 2 pi, n. Those are the only things that don't really cancel. And sine of 2 pi n, and remember n, where is it? N is integers. 2 pi n is always equal to 0, so this bit dies. So we end up with 2cc star l is equal to 1, and so cc star is equal to 1 over 2l. Okay, not useful because I want to know what c is, not cc star. Okay, so because this nasty thing is complex, and I want the whole prefactor to be real. So I get a real solution to the Schrödinger equation. So it's physically relevant. Since I want that whole thing to be real, and I've got an I there, which is clearly not real, I want C also to be complex. Okay, so that's my justification. So I've written out C as being equal to alpha plus I beta, just in terms of a complex, C being a complex number is equal to A plus I beta, and A minus I beta is the complex conjugate of C, blah blah blah. So that's my justification for saying alpha squared. I've just expanded this, by the way, and that's 1 equal to 1 over 2l. I've expanded that. My justification for saying that alpha is equal to 0 is the fact that I want a real solution. So that's just what I just said. And beta is equal to 1 over square root of 2l, because alpha is equal to 0, so b squared is 1 over 2l, so beta is equal to 1 over square root of 2l. Okay. And of course, c is equal to alpha plus beta, I beta. Alpha is 0, so c is equal to 1 over square root of 2li, which is what I wanted. So I worked out what c is here. Great. Okay, substituting that in. Thankfully the i's go to -1, and the -1 cancels with the other negative to make +1, and we get and 2 over root 2 is equal to root 2. So we end up with a prefactor being root 2 over L, sine of that thing. All I've done here is I just thought, well, I've substituted that where's energy? This thing here, which was derived earlier, energy, back into this, and we end up with a nice solution. Square root of 2 over L, sine of nx pi over L, which is the nice solution from this diagram. Some sine of nx pi over L. So a load of sine functions. And I've drawn 10 of them. I've drawn sine of x, sine of 2x, sine of 3x. They're all here. And of course, the size of my box, if you're interested, is going to be equal to pi. Just to make this drawing nice. So those are the solutions as graphically we might expect them to be. Okay. And of course it can't be as simple as that, because this differential equation, this time independent Schrödinger equation thing here was linear, we can have any arbitrary combination of solutions. Wave function here. We can have any arbitrary combination of solutions. So the fact that we have a solution in terms of n, and this is why, incidentally, I've been writing these wave functions with a subscript n here. So I haven't gone mad. These are the reasons why I've written the subscript n here, just to make it clear that this isn't the most general solution possible, because we've only worked out the solution in terms of different values of n, but you can take any linear combination for the reason I just said. You can take any combination of n. Basically, this means that you can add together these wave functions on the graph. Okay. Okay, so this is in a box. This is the wave function, the solution of the wave function. I've written 0 otherwise because this is the solution inside the box, and of course we've already said that the wave function outside the box is equal to 0. Not forgetting the fact that the time dependent wave function is equal to the time independent wave function times by the time part, which we derived all the way over here as being a e to the negative eti over h bar. So all I've done is I've multiplied that through. Of course, the a's disappeared, which is the a is going to be disappear because this wave function has already been normalised, so the normalisation constant was already found to be root 2 over L. The idea is that if you integrate it between negative infinity and infinity, this thing here, it's got to equal 1. So A turns out to be 1 anyway, so A disappears. So we just get this time part here. Obviously this is multiplying through by 0, so we can just have that 0. Okay, so this is the time dependent wave function, okay, but not the most general one. So as I said, it can be written in terms of linear combination of different n's, different values of n. So this is why I've got different values of n here, and this Cn is just a constant, the fact that we're multiplying each sine one by the inside part of the wave function here. Okay, for convenience sake, I'm going to stop using n and I'm going to start using q, just to keep things looking as unhorrible as possible. And so of course this should be CQ and not CN. Sorry about that. Okay, so when t is equal to 0, this time part disappears for convenience. So this is the initial time dependent wave function. The wave function when t is equal to 0. This is the full thing here. And I've ignored the part where 0 is everywhere else. This is the part inside, of course. So really there should be a little thing telling me it's inside, but you know it is. Okay, so the idea is to find Cn here. The way you can do it is by multiplying the complex conjugate of an arbitrary wave function. So instead of m, we're going with p. But this is just the same. It's the same quantum number. It's the same thing. It's just I'm just writing. It's just a different number. If you get what I'm talking about. So multiplying that by this thing here. Okay, integrating between L and 0, and of course this is just the like what we're doing here. So integrating between L and 0. And you get this horrible thing here. Okay, so this part here is just going to be the thing that was derived here, so it's just going to be this, of course, with p, because my subscript is p. This is in terms of the quantum number I'm writing it as p here, and then the initial wave function is this thing here, and I've written it in terms of q just to make things nice. So we've got so these are different integers, of course, or they might be the same. They're just written like this. So we've got a sum here and two bits here, and of course, since it's an integral, you can put this inside the sum. There's nothing wrong with doing that. This is just multiplying through by the sum, so I can put it inside if I want to. So now I've got sine of qx, and I've actually written them in the most confusing and horrible way around possible. But anyway, these two are multiplied together. So I've still got CQ here. So I've got sine. I've got the sine of the Q1 and the sine of the P1 multiplied through by the square root of 2 over L on both bits here. Now I'm not going to prove this. I think I did prove it in one of my earlier videos. It was proved in the video about the infinite series for pi, the one where I did the Fourier series stuff. It's not difficult to prove it, but it's incredibly tedious, and it involves a load of trigonometry, and I can't be bothered to do it now. It turns out that if Q does not equal P, because these two signs are sort of orthogonal, they integrate to 0, and this is what this thing is saying here. It's saying that if they're different, it's 0, but if they're the same, if P equals Q, it integrates to 1. With the square root of 2 over L factor, making sure that it integrates to 1, because obviously when you integrate the sign, some horrible factor will come out, but these square root of 2 over L, we've already shown that they're the normalisation factor that makes it go to 1. So you end up with just the CQ times by this thing, which is determined by whether P is equal to Q. Of course, since we've got CQ here, this only works if P is equal to Q. This is only 1 if P is equal to Q. We're summing over Q, so this is only going to integrate to something that isn't. This is only going to become something that isn't 0 if Q is equal to P here. So this is going to be equal to 1. So Q's got to be equal to P. So we've just got the P term, so that's equal to CP. And we we can just do an arbitrary change of variable to get Cn. We can just say n equals p, or something like that. Basically, we've worked out what Cp is in terms of the initial wave function, big psi x, comma 0. So the general solution is Cp is equal to this thing here. So we said that Cp is equal to this thing here, this thing times this thing, so Cp is equal to this thing. Okay, so we said that the general solution is equal to Cn times this thing, so this is this bit here, and then this horrible thing is all of Cn. We said that Cn, or Cp, whatever, is equal to this, which is the integral of n. This thing we said is equal to this part here, so that's sine nx pi over l, and then multiplied by this, which you could also write in this way if you want to, in terms of the sum of these things, but sometimes you just want to write it in terms of the initial wave function that you know. So knowing the initial wave function, you can work out what Cn is. So this is the most general possible solution to the 1D particle in a box problem, and it's horrible. But the maths used in deriving it wasn't hard as such, it was just tedious. So this is the solution. I hope you enjoyed this horribly long and video where I used the word arbitrary too much. Thank you.